Permutation equivalence equates sets whose elements are exactly the same regardless of their order. Without p-equivalence, sets such as 1, 6 and 6, 1 are two distinct points. However, once p-equivalence is applied, we no longer distinguish between the two, effectively changing ordered pairs into unordered pairs. When beginning to visualize the effect of this equivalency on a two-dimensional plane, it is easiest to begin with the simplest cases. In this instance, these would be the sets which contain only a single element that is repeated. The set xy, where x is equal to y, will not have any other points mapped onto it through this equivalence. The collection of all these points forms the line y equals x, which will actually be the boundary of our space. The x-axis will map onto the y-axis. The point 0, 12 will move to 12, 0. We will also look at a few other sample points, 4, 1 and 10, 3, just to help us visualize the motion. Anything below this line will have a corresponding point above the line onto which it maps. Therefore, the resultant quotient space could be represented by the relationship y is greater than or equal to x. The application of p-equivalence to O space is slightly more complicated, but if we start with p space and fold it into the torus, we will be able to understand it better. The boundaries are the x and y axes, which are now the same line, and y equals x. We can also apply p-equivalence after folding the space into a cylinder. This is just used in order to help conceptualize the final process. Now if we start with a torus, O space, and apply p-equivalence, we can see O space moving to OP space. Musically, this concept allows analysts to look at collections of pitches regardless of the order in which they come. This is especially important when looking at harmony. Without p-equivalence, the set of notes C, E, G would be different than if they were arranged C, G, E.